I'm Iskander, but everyone can call me Alex because it's simpler, especially to pronounce. About me. Well, I think I can describe myself as an open source developer. I work in open source both at my spare time and at my job. And my primary projects I work on is Golang Go toolchain itself and GoCritic linter and everything that used to build that linter. So there are libraries that were used while this linter was developed and some other stuffs like that relate to me. And the reason why this talk exists is that performance, it matters for some people. And if you have some abilities to make your program run faster because hardware supports some instructions, you want to use them. Otherwise, you are paying for the hardware and not using it and wasting your money, essentially. And to demonstrate the difference, for example, there is a bytes index function, and you can implement it in pure Go using a loop and finding the byte in the slice. It works, but it's very slow. It's slow not because it's intrinsically a bad algorithm to find something inside a slice, but because it doesn't use anything that built into the hardware to make your code run fast. If you implement that function in the assembler, it's like 20, 30 times faster, and it's a big speed up. So to make your program run faster, there are different kinds of parallelism, and you generally want to use every one of them to make your program maximally fast on your hardware. But not all kinds of parallelism applicable to any kind of algorithm. Sometimes you use either of them or two of them. For example, in Go, you can't use data-level parallelism because the compiler doesn't generate any single instruction, multiple data instructions. So your code is never going to use these speedups unless the function is implemented in the assembly. So this is the reason why in the Go we have assembly code to use those instructions. And if you're interested about that, why Go compiler doesn't generate newer instructions, there is actually an issue, like a proposal to make there is a environment variable that you can use to tell the compiler, I want the newest instructions used in my binary. So you can use them, and your binary will be less portable. You can't use this binary on the older machines, but if you're running it on the same machines that have same hardware, they will work faster. So essentially, you have to write assembly code, and writing in assembly is usually depressing. You understand the program when you write it, and you have the algorithm in your head. Sometime passes, like a week, and you can't understand this code. You can't debug it, really. You have to learn it again. You have to look up the algorithm. You have to read comments that explain what this code does. And if these comments get outdated, you have to read the assembly. Comments are lying so frequently there because humans make mistakes, especially in assembly programming. So we want to use those accelerating instructions while not writing really much amount of assembly. We have to say that we want some assembly, like I want to use this instruction that makes parallel multiplication of a matrix, for example. But we want to have Go code in our programs. It's like if you don't have something that looks like Go and use only assembly, you have to write the whole algorithm in assembly. And there are many issues with that. And if you have something like intrinsics, like in C programming language, you can use expressions or some types that help you to write the machine-like code, but it's more maintainable. And you concentrate the code that should be fast in the less scope of your code. So this single instruction multiple data is the key success here, why the index bytes is faster in assembly. And for example, suppose we want to implement a library that uses the assembly, but it exports Go functions that can be called from the code. So we not have to use the assembly, and we can just call the function that is implemented in the assembly. And you can implement the truncation function from the standard library like this. It's not hard. You can even write something like this. It works the same way, same performance. and we should benchmark it whether it really works fast. The answer is it doesn't work as fast as it could. It gives some performance improvements over the Go code, but it really, you're paying the cost of the calling function. You can't inline assembly, and you're doing much more work. So, but the math bits package is very special in Go because compiler doesn't understand all functions from there, and it doesn't really generate the function calls. All it does is inserts the SSA representations into your code. So it knows those functions. It was taught to understand them, but you can't extend that. It knows fixed amount, very few functions that are efficient. You can't write your own math trunk. And why? Basically, these are the reasons, because there are more work needed to do. And note that even though that code is faster, it does actually useful work. The standard library intrinsic, they check whether your processor supports those instructions. If it doesn't, it will work like a Go function. So they have Go implementations in them. So it does portability plus performance. So your library is going to be very bad. ABI changes like register-based calling convention can help, but it wouldn't remove the call overhead. It will be still there. So writing assembly is not an option here because we want to write less assembly. And there are several ways to achieve our goals. For example, you can avoid such optimizations and say we can buy more hardware, we're giving up. We need sufficiently smart compiler that can auto-vectorize your loops, but it can even not happen because even in C++, where there are no constraints on the compile time, not all loops are vectorized. You sometimes need to give some hints to the compiler, like this loop is parallel, giving some pragma or magical comment, or using some intrinsics yourself. There is another way that is preferred by the Raskox, I think, like let's collect all functions you need, and we just add other packages like math bits without giving any new mechanism. It's like we're just giving another package, and that it's very special to the compiler, it doesn't matter. But the problem that this doesn't scale, and to request a new function, you have to go through the very long process, and you're not guaranteed to success. It can be rejected. So you can never get what you want, really. So maybe we want something like real intrinsics. And here are some slides that describe every alternative ways to implement intrinsics or inline assembly. All those methods are like you're writing Go code or C code, if we're talking about C intrinsics. But in places where you want to use machine instructions, you specify it this special function. Or in case of inline assembly, you're writing small piece of assembly code that is when connected with Go or C code. In our case, it's Go code. In case of inline assembly, like in GCC, it's really hard to maintain. Intel C compiler implements intrinsic, like it gives you 5,000 of functions. It's like this. So there are so many functions, there are many types. It doesn't really pleasant to use, and it's kind of hard to push that package into the standard library because it's kind of mad. Rust gives you more conservative intrinsics. They are like high-level operations over the data. So there are like 200 of intrinsics, but like in Go, it's very limited. Maybe there are nothing you need, really. So the proposal I was writing and implemented the prototype for is like this. You have only one function, and you pass into that function the opcode name and the arguments. Arguments can be arbitrary Go values, like it can be constants, it can be expressions, anything you can use in normal functions. It's like a function, but it's handled like intrinsic. So we are adding one real intrinsic in Go terms and one public function. So less symbols, only one function, and it can express almost 99% of instructions. And the benefit is that this scales to any architecture. Any architecture in Go can support this feature. And if it doesn't, well, you have to guard with some build tag. But if you're using assembly, you have to do it anyway. As unsafe package is chosen because it really states that it doesn't have portability guarantees like other packages. If you look at the documentation of that package, it says so. So we can add a new function there. And also, if you're using assembly, you most likely will need unsafe pointer to do some pointer arithmetics. So if you're already importing that package, maybe it's not that breaking to have one more function. They're useful in combination. What do we get by that proposal? Basically, writing assembly is hard because there is almost no tooling support. You have to write in some text editors that doesn't even auto-format your code. There is awesome FMT, for example, but it really works so bad. And it looks like it doesn't even maintain. So basically, most review comments are about formatting. Because if assembly is even bad formatted, it's not readable at all. If we're moving assembly into the Go and it's a normal function, we have all benefits of Go, and we can jump to awesome function, get its documentation, for example, and we're still in the environment we use for Go. So it's easier for Go programmers to read and write. And by the way, we can implement the third-party library, like intrinsics, which wraps this unsafe awesome call and gives you some signatures, what arguments are expected, what are the types is. The benefit is that it can be implemented as a third-party library. It doesn't have to be inside the Go. The second goal is to clean up the compiler, get rid of the special handling on the several functions. This approach doesn't scale very well, and this intrinsic-like inline assembler can be used to implement those. And it's fast. It's almost the same as the assembler. In some cases, it's a little bit slower because in assembly you have very crazy control flow. You can do really mad things there, like doing some arithmetics and then jumping using the flags that changed during the last operations. And it's inlineable, so there is no disadvantage like being a function call there. So it's same fast as assembly. And it's like a hatch into the compiler. We can insert some some instructions into the code. It means that the external code processor can actually insert something there, like vectorizing your loop for you, and you get the Go code that is compiled by the standard compiler. So you don't have to use different compiler. It can be like external optimization. And another thing about tooling is that you have linters, and we can write linters for Go, and granted that we have very great libraries for that, we can write a linter for that unsafe awesome. And here is some example how it looks like. It's like function call. You specify the instruction and then operands. This is the variable, so you don't have to take address. It figures out that it lies in the register, for example. It uses that register. You don't have to use registers. You can, but you don't have to. It's not very simple to read, but it's like a foundation. You can wrap this into the functions, give a pretty interface. It's just a really hatch. And truncation functions from the example can be implemented like this. You don't have to use assembler wrap. This time you don't. You just write this, and the same assembly code is generated, same performance. Implementation is kind of tricky because it's not many lines of code, but it moves some parts of the toolchain into different places. So many imports are rewritten, but user don't see this. So the problem is the more difference in patch, the harder it to protect to merge into Go. And there was some accidental things, like in order to pass this, we need assembler passer, because you can use here the assembly memory addressing operations here, like indexing plus scaling, it works here. So parser is moved. GC compiler has awesome function. SSA is taught to understand this, and register allocator properly handles those, so you can use them quite safely. It doesn't clobber your register. So if you use some register, the code Go generates for other code that is not your unsafe awesome. It doesn't use the same registers, so it allocates correctly. and there are some changes to the code generation. So the proposal had some upvotes, but it has some downvotes from the core team. So it's what matters. The core team does accept something. And it has some support. People want some ways to define the user-defined intrinsics, because even though Rust Cox thinks that it's really possible to add more functions to things like math bits, you can't express any operation using this approach, because not all operations maps to the one function, one instructions, and not even on the different architectures. The proposal actually is closed now, and this is not going to be merged. And this is like a failure, but it had some lessons. There is some attention to it, there is some demand, but the fraction of the people that needs it is small, like less than 1%. But if those people doesn't have this, they can't give you libraries that perform as fast as Go standard library, because it's written in assembly, essentially, for example, this index byte function. So you have to either write your own assembly or use other assembly. There is no way to use Go in this. Here is a list of concerns. I already mentioned some of them. And the most important concern is like you have a third way to express your algorithm. There is pure Go, there is assembler, and there is some mixed kind of programs that use both. And this is a concern because Rust believes that if you want to write a performant code, use assembly. This is your way. If you doesn't care that much, you can use Go. This is a good point, but it's unlikely that you have a better compiler that can vectorize loops in like 3 years, or maybe it will never happen because it needs complications and increase in compile time. I don't know if we're going to lose like 2 times of compile time in favor of some speedups. And we don't have flags. Go usually doesn't have flags. We can't tell the compiler, give more optimizations, I don't care about the compile time. There is no such flag. If there was some, maybe we had vectorizations already by this moment. What we can do next is to figure out the solution that doesn't require you to merge these 2 worlds and still get the benefits. For example, we can annotate the assembler code with some special magic comments that give some hints to the compiler how to generate SSA representations from this assembly. This can get your assembly function inlineable. So we remove the main bottleneck of the assembler, and we can write small assembly functions. If we can write small assembly functions that are inlineable, we can wrap them in Go functions. So I'm still looking for a better solution, but the best I got is like annotating the assembler, but it removes the benefits of toolchain support or tooling. It's harder to maintain the assembly code because there are less editors or IDE support, especially for Go assembler. It has its own assembler. So the tools that work for other assemblers doesn't work for Go, for example. Maybe there will be some kind of another distribution of Go, like Intel Go, but it's not guaranteed. We can do it, but why? Not everyone is going to use the custom distribution of Go, and you have to recompile your program with other compiler. So it's not like we're implementing our compiler, it speeds up your program magically. And by the way, it can be a good field for experiments. For example, we can actually merge this prototype into that repository and people can try it. For example, reduce their amount of assembly to measure how much performance they lost, if any. But it has some maintenance cost. For example, if this feature is never merged, and it's unlikely that it will, time is wasted. So someone have to experiment, but people are not very willing to do so. So maybe it's the end, but that proposal is not over. there will be second and maybe third, and at some point maybe we will meet the place where we can use the benefits of the hardware while not writing so many code in assembly. It's hard to give some 100% promises, but as the time passes, we record what was rejected from the previous proposals, and every other one doesn't have these disadvantages. And at some point, the disadvantages should become so small that proposal should go through. And if it doesn't, it means that there are some non-objective reasons that it doesn't get into Go. So it's going to be interesting. Thanks.
So do you have any questions?
Thank you very much for your talk. I want to ask you about your experience of communication with the Go core team. Well, basically, what do you feel about it?
It depends on who you're trying to communicate.
Russ.
Russ? He's very busy.
Sorry?
He's very busy. You can't really communicate with him frequently. It's like one mail in 1 or 2 months with this short letter. So that's it. Usually he answers in the public places, like the issues on the GitHub, so he answers the question to everyone. So it's really hard to communicate with that part of the Go team.
But are you happy overall? Are you happy with your communication overall?
We're kind of independent in some ways. For example, I myself maintaining the Go AMD64 assembler and the compiler part that optimizes for this architecture. And Russ doesn't really interested in such low-level things. He now works on very high-level language design or the future of the Go and modules, for example. Those parts are very low level, and only compiler team interacts with us more actively.
Thank you.
More questions?
Thank you for talk. The question is more like specific, returning back to assembly instructions. When we are working with, with all the values, writing an assembly code, is there any performance difference between using registers and opposite to variables when you're storing some values?
No, it's actually better to use Go values. If you use register, it makes harder for the register allocator to allocate the register efficiently. It has to be conservative. But if you use specific register, it needed for specific instructions. If you want to do some really interesting stuff, like having several fields of your vector registers having different values. So you can't have this in the Go variable. You have to put it into the register because there are no types that represent the 512 bits of vector.
I see, thank you.
Thanks very much for the talk. I have like a question about runtime. Are we talking about like Go assembly, like a free format assembly, or are we talking about like the same assembly that has the same guarantees as the Go ASM? So it shouldn't break your runtime at any cost, as you shouldn't have like a pointer to a pointer and all these things, or will it be like complete free format assembly?
Are you sure Go assembly has any guarantees?
Well, like theoretically, I assume like if you have a GC and manage runtime, you should have some guarantees because like your addresses can be moved, your objects can be moved. So will it have some guarantees on the runtimes? No. So
the assembly you write in Go using the assembly, you have to maintain those guarantees yourself.
Sure, yeah.
And this is the same. There is no defense shield in here. You're on your own. You don't have to have pointers in registers that can outlive some value. It's dangerous.
Yeah. Okay, and then probably the next one. The next question is, what about like portability? Like at least when you're creating an assembly code, you got like different files for different architectures. But what about like opcodes inside the code? Will you have like multiple functions and only one of them will be compiled? Or like what about like embedding it into your source code?
You can use two different approaches, just like this assembler. For example, you can have the several Go files with suffix. So it's the same like having assembler with suffix of the AMD 64.
Yeah.
Or you can have one Go function that has different bodies depending on the architecture.
Okay, yeah. Thank you.
It's adds some cost to the maintenance, but the assembler does the same. If you write machine-dependent code, you have to think about it. But the best part of this thing is that you can write a library that encapsulates this, and you have API that doesn't force you to use build tags. Depending on your architecture, the functions are exported from the package will be different.
Okay, yeah. Thank you.
I have time for a couple more questions.
And thank you for your presentation. It's really incredible proposal. I like it because it gives you so much power over the stuff. The only thing I'm very worried is about people starting creating shitty libraries and poisoning all the Go ecosystem that we have now, because now if I want to use library, I'm pretty sure it's memory safe, it doesn't have too much problems. Can your proposal actually, can people using your compiler, the Intel Go, make such libraries that could just segfault my binary?
It was the idea that with this proposal accepted, we could implement that library. So other people probably shouldn't use this low-level mechanism. Standard library could, but it difference from the user's third-party library and standard library. It can use it there, and there can be a public library, like in Golang X, intrinsics, that is very friendly to use, that is more safe, but it's still like assembler. You have to think what you're doing. If you don't understand what you're doing, it can be fixed. This proposal.
Oh, yeah, I understand. So basically we say everything that is /x package is going to be included in the, maybe allowed, but if I create some code, it's not going to work. Because I mean, I just want to be sure that my program is safe. How do I make sure that?
You can be sure.
Okay.
Runtimes also have bugs.
Okay,
Compiler also has bugs. You can be sure for some percentage.
More questions?
Thank you for your presentation. I just want, I really like this example when you show when you can use assembler in Golang.
Which one?
Yes, this one. I just want to know how I can get it. How I can use it, play with it.
How can you use it?
Yeah, and it's been like how I can use unsafe ASM right now. Like how I can
Right now, the prototype implementation wasn't pushed to the GitHub yet. It could be, but it requires some polishing.
Okay, but can I compile by myself?
Yeah,
Yeah.
I think so.
It's been like just to get this purpose and like.
You need code. I can give you the implementation,
Yeah.
and it will be published in the GitHub in some near time.
Okay, this is what I want to know. Thank you.
Thank you for the presentation and for your job. It's really awesome and amazing for me. First time when I saw something similar, it was Free Pascal. And my proposal, you're right, we need something, in my opinion, personal opinion, we need something like inline comments instead of call, package, and function, because it's more readable.
Inline what?
comments like awesome and then just poor awesome code. Did you saw something similar in other languages?
I think they doesn't use comments for this.
In my question, is this possible to implement?
The Go team doesn't really like magical comments. They're adding some stuff there, but there is big threshold what we can add. And when I was talking about magic comments in assembly, there is a difference. So it's easier to add some magical comments into the assembly files than into Go. The assembler doesn't have same guarantees like Go. It's kind of different language. It's not even specified.
Yeah. But if you want to use awesome, you should be sure that you know what you're doing.
I mean, it's not about what you know what you're doing. It's about the Go team doesn't want comments to become more magical. We have
just
directives, but that's enough.
Ideology. It's just ideology, I think. Okay. I see. Thank you so much.
You can have alternative implementation of Go that supports this.
Okay, thank you.
All right, I guess that's the last question for Iskander.
Hello, thank you. I have one little style question. Can we have next slide with free and safe? Oh, with free and safe .asm comments. Yes, that. We have three goals of ASM that look kind of but readable and boilerplate. Can we make multi-comments per one call? Like we have save ASM new line first comment some special arc like new line in our code, next comment and other. So we can call unsafe ASM only one time and have many comments. Maybe it will be more readable.
It's possible. For example, you can have a very big function that has sentinel objects that separate the arguments, but I'm not sure it's really more readable than this. Usually you don't have more than 3 or 4 instructions in a row. Usually it's 1 or 2, and then you have to read some flags, store it in the Go value, and then use Go value. Yeah, it's really possible, and it's also possible to have one string argument. The entire string can be here, and the compiler will pass it on the compile time, but it's harder to maintain. You can't jump to values. Here, you can jump to X variable here, so it works.
Thank you.
Thank you so much, Iskander. If you have some more questions for him, you can catch Iskander while drinking coffee or anywhere, any place else. So, which was your favorite question? Who will get the T-shirt?
Now I need to remember all the questions.
Yeah, there were many. Hard choice.
I think the one which raised the concerns about if we have this feature, there will be more unsafe ASM in the wild. This was one of the concerns why this proposal is rejected. I think you asked this question. Okay, so who also asked questions?
Raise your hand who asked questions.
I think there was another. Yeah, you.
Yeah, he's the lucky winner. Come over here.